The topic of this video is thermodynamics. We've already looked at thermochemistry, which is the study of heat in chemical reactions. Remember, heat is the transfer of thermal energy, whereas temperature is a measure of the hotness or coldness of a system. So thermochemistry is the study of heat in chemical reactions. Thermodynamics is the study of the interconversion of heat and other kinds of energy. Thermodynamics is the study of the interconversion of heat and other kinds of energy. And you can think of some other kinds of energy. There's kinetic energy, the energy of motion. We won't be dealing too much with that in this chemistry course, in this chapter, but we can talk about the motion of gases as they expand or contract. We'll be looking at that briefly. There's potential energy. Usually when you think of potential energy, you think of something being raised to a higher elevation. It's lifting a book off the table. It's now getting potential energy in relation to its ability to fall closer to the center of the Earth due to the acceleration due to gravity. We won't be dealing with that at all in this discussion. There's electrical energy, and we'll talk about that in Chem 112 when we again talk about oxidation reduction reactions. And of course, there's chemical energy, the energy that's stored within chemical bonds. And that will be something we'll very much be talking about as we go through this chapter. So the three types of systems, when we talk about thermodynamics, it's important that you understand these. An open system can exchange mass and energy with the surroundings. For example, here's a flask that's open to the atmosphere. It's not stoppered. And so water vapor can escape or enter the flask, and heat can enter or leave the flask. A closed system allows for the transfer of energy but not mass. Now we're going to take that same flask, put a stopper in it. Now water vapor cannot leave or enter the flask, but heat can still enter or leave the flask. So that's a closed system. An isolated system does not exchange either mass or energy with its surroundings. So no water vapor can leave or enter. No heat can enter or leave, because in this system, not only is the flask stoppered, but now it's insulated. Think of that as like being a styrofoam case around that flask. You're just looking at a cross-section of it. So three types of systems: open, closed, and isolated. Another important concept to get a grasp of are state functions. State functions are properties that are determined by the state of the system, regardless of how that condition was achieved. All you care about is where you start and where you stop. So the magnitude of the change depends only on the initial and final states of the system. And so here's an example of a building. And if you talk about the change in elevation, all it matters is where you start and where you stop. You can go over from the first floor up to the fourth floor, or the ground floor up to the fourth floor. The ground floor, we'll say you're at an elevation of 0. Fourth floor, let's say you're at an elevation of 40 feet. And so that change in elevation is 40 feet. Now, you could have gone all the way up to the 6th floor and then come back down to the 4th floor. But being a state function, all you care about is the final and initial states, and so that change of elevation is 40 feet. However, if we're talking about distance traveled, that's not a state function. If you've gone all the way up to the 6th floor and back down to the 4th floor, you may have traveled 80 feet in all. And it depends on how you get there to the 4th floor. But in a state function, all you care about is your elevation, your change in elevation, and that can only be 40 feet. So what are the types of state functions that we'll be looking at? There's energy, there's pressure, there's volume, and there's temperature. So those are the state functions that we will be most interested in as we explore this material. So the first law of thermodynamics is something that you've heard about for many, many years. It's also known as the law of conservation of energy. The first law of thermodynamics states that energy cannot be converted from one form to another. The energy can be converted from one form to another, but cannot be created or destroyed. Energy can be converted from one form to another, but cannot be created or destroyed. So let's talk about U, and let's define U to be the internal energy of a system. And so delta U is the change in the internal energy of the system. That triangle is a Greek capital D, or delta. So that, going back to remember that the system plus the surroundings equals the universe, one of the first definitions that we learned about in this material. So the change in the internal energy of the system plus the change of the internal energy of the surroundings equals the change of the internal energy of the universe. But law of thermodynamics says the energy cannot be created or destroyed. And so the change of the internal energy of the universe is equal to what? It's equal to 0. Hence, this expression that you see on your screen, that the change of internal energy of the system plus the change of internal energy of the surroundings equals 0. So the subscripts cis and sur denote respectively the system and the surroundings. So change in internal energy, the final internal energy minus the initial internal energy, is what delta U is. So delta anything is going to be final minus initial. Remember that. The change in any system that we're looking at is going to be the final minus the initial. And so if we rearrange algebraically the equation up above, the change of the internal energy of the system equals minus the change of the internal energy of the surroundings. They're going to have the same magnitude, the same size, but they'll have opposite signs. And so we're going to define our way of talking about this to be the change of the internal energy of the system is equal to minus the change of the internal energy of the surroundings. This definition will come into play momentarily. So the overall change in a system's internal energy is given by delta U is equal to Q plus W. Delta U is equal to Q plus W. Q is heat, and W is work. So, using our definitions, delta Q is positive for an endothermic process, energy absorbed by the system. Delta Q will be negative for an exothermic process, where heat is being released by the system and it's going to the surroundings. W is positive for work done on the system. And W is negative for work done by the system. So my little memory device for trying to remember this, sort of think of Q as money and W is effort. And so Q, if it's money, you like to get money. Like money coming in. So if it's positive, and that's a good thing, money coming in, so that's going to be positive. Whereas if you have to pay, money's going out, that's negative. So if Q is positive for an endothermic process, Q is negative for an exothermic process, where heat or money is being given up. Think of W as being effort. You'd rather expend as little effort as you can. You'd rather have someone else expending an effort for you. So work is positive, or effort is positive, when it's done on the system, when it's done for you. Whereas work is negative for work done by the system, or effort that you have to exert. So that's my little handy-dandy way of remembering the way to assign the signs for heat and work. So delta U is equal to Q plus W. heat plus work. And so here are the sign conventions once again. So if heat flows into the system, Q is positive. That's an endothermic process. If heat flows out of the system, Q is going to be negative. And that's going to be an exothermic process. If the system's doing work, what we're looking at is a piston here. The gas is expanding. So the system is doing work on the surroundings. And so we're going to define that as work as being negative. And so the volume of the gas is increasing in this instance. Whereas if we're compressing the gas, work is being done by the surroundings on the system. We're going to define that as positive work. W is going to be positive. So make sure that you have these sign conventions well understood. Thanks for listening.